All right, so we're going to go on with our counting discussions today. We're going to talk a little bit more about other ways to count, maybe in a more involved situation. So permutations that have either repetitions in them, or what happens if we put things in a circle instead of a line. So we're going to talk about some of these other unique situations. I'm going to start you off with an example. So I'm going to kind of skip the thing at the top, the box. I want to talk about this example. It says, how many 9-letter patterns can be formed from the letters of the word nonlinear? To be a little bit math nerdy here and use a math word. So nonlinear. Well, first of all, how many letters are we choosing from? So let's just double check and see. How many letters do you have in the word nonlinear? So go ahead and count those. Looks like there's 9. So why did I make you count that? Well, when I say how many 9-letter patterns, well, if there are only 9 there, great. So then that's the number that we're choosing from. But what if the number of letters was more than that? Then we would be doing like a permutation or a combination like what we talked about yesterday. We'd be choosing from a larger group. So you need to make sure how many you're starting with always. So kind of that total number is important. So yeah, there's 9 letters there, so how many patterns can we make with those letters? So I think what we would have talked about yesterday is think about, or the last time here, when we talked about just regular permutations and how many ways can we do things, counting, we have 9 letters, so 1, 2, 3, 4, 5, 6, 7, 8, 9. How many options do you have for the first letter? Well, 9 of them, and then you would have 8 and 7 and 6, 5, 4, 3, 2, 1, and the counting principle says to figure out the total number of ways you can do something, or each individual thing to get the total weight all together, you would multiply them, and we talked about what this was. What do we call that? Well, that's factorial, right? So that would have been 9 factorial. That's how many ways you could arrange 9 things in a line. Problem is, and maybe you've noticed this already, look at this word, we have some things that are repeated. We have ends that happen more than once. Okay, so I want you to watch something. You have to watch super carefully to see if you can tell what I'm doing here. So nonlinear was the original pattern that they gave me. I'm going to rearrange the letters and write a new pattern. So watch carefully. Are you watching? I wrote a new word. I switched the letters. What did I do? I switched the ends. Could you tell? No, but I did. How do you know if I didn't, right? Because it's the letter is, or the pattern is exactly the same. So you have to really be careful with this. If you have repetitions, I can rewrite it and rearrange things, but I get the same pattern. So think of like passwords or codes or things like that. So when you're looking at how many different ways can you rearrange, if you're repeating stuff, that's going to give you exactly the same passcode. So it's not going to be any different. So we have to divide out the repetitions. So I can't just do 9 factorial. I need to divide through by the things that are repeated. So in this case, there are 3 ends. How many ways can you arrange 3 ends? Well, you'd have 3 choices, then 2 choices, then 1. So it'd be 3 factorial. So the number of ways to arrange 3 ends would be 3 factorial. So when I divide these then, I'd end up getting 60,480. So I'm going to have you doing a little bit of that arithmetic kind of on your own. The more important thing is figuring out what factorial is that. So if you have things that are repeated, we don't want to count that pattern or that pass more than once. All right, so let's take a look at another one. So how many 12-letter patterns can be formed from the word mathematical? So again, double check how many letters are actually in the word mathematical. So go ahead and count them. All right, so 12. So that's good though again, because if there were more letters that we'd be choosing from, I need to know that if my selection is going to be less than that. So there are 12 letters. So if I just had all distinct different letters, there'd be 12 factorial ways you could arrange it. 12 choices, then 11, 10 on down the line. Now what we have to be concerned about then is what if we have repetitions? Okay, well, if we have repetitions, like we have 2 m's, I have to divide out by the number of ways I can arrange 2 m's. Technically, it's 2 factorial. 2 choices for the first, and then 1. All right, well, what else do you have repeated? Looks like A's. Looks like there's 3 of those. So 3 factorial ways I can arrange the A's. And it looks like I have 2 T's. So I'm looking at the things that are repeating. 2 M's, 3 A's, and then the 2 T's. So 2 factorial for that. Now, when you're going to type this into your calculator, let's talk about strategy here. It's really kind of a hassle to get the factorials. I know we talked about that it's under the math menu. If you arrow to the left, you get there faster under probability. But still, doing that 3 times in the denominator would be kind of a bummer. So Let's think about if there's a faster way. What is 2 factorial? Well, that's just 2. What is 3 factorial? That's just 6. And then 2 factorial is 2. How about instead of typing that whole thing in, how about you do 12 factorial divided by 24? For me, that would be a lot faster. So think about ways you can make that calculation part of it easier for you. Because if they're easy numbers, those are going to be pretty easy to put in there then too. So repetitions, we have to be careful. If things are repeated, we're going to be overcounting. Okay, so the next thing I want to talk about is the idea of putting things in a circle. In class, I'm actually going to have people stand and do this. But for right now, I'm going to talk about and just kind of show you with pictures as best I can so you can get that representation. So does it change the number of options we have that are distinct or different if instead of putting things in a line, like books on a shelf or people in a row or letters in a word or a passcode or a code, what if we put them in a circle instead? Does that affect the total number of ways that would be considered distinct or different patterns that we would need to count? Well, let's take a look at a picture. So what I'm going to have people do in class is I'm going to have them stand in a circle holding letter signs. So they're lettered A, B, C, D, E. Now, if I just rotate those one spot, so I rotated the A one spot clockwise. Is that still the arrangement, same arrangement of people around the dinner table? Are they sitting at the same location with respect to one another? The people who are across from each other are still across from each other. Everything's the same. And I could do it again. So I can move the A one more. All right, so there's another one. Still the same ordering, right? Same people in the same spots. I can move the A one more. Is everybody still in the same spot, same location with respect to one another? Can move the A one more. So now we're on our 5th rotation. And again, people are still seated at exactly the same spot with respect to this table going around this circle. So when I look at So all 5 of these orientations or rotations are all the same ordering of people. If we counted all of these, we're counting the same grouping of people in the same order 5 extra times. So when we think about circular permutations, what we really have to go back and think about is it's not just the same as putting 5 people in a line, or I'll do this work up here, 5 factorial. What we'd have to do is divide by the 5 ways that we can just rotate them around that all look the same. So when we think about 5 people in a line, it is different than 5 people in a circle. So 5 people in a line would be 120. We're only going to have 24 different ways that we're going to be able to do that. So arithmetic wise, there's much fewer. Now let's talk about what the formula looks like then. So they are saying up here that you can do n factorial divided by n, which is exactly what I just did here. 5 factorial would be 5, 4, 3, 2, 1. And if I divide by the 5 ways that those people can be just rotated, then I get my 24 ways that I had. So that's that n factorial divided by n. That's one way to think of it. But some people think of it this way. Well, I can divide the 5s out. That leaves me with 4, 3, 2, 1. That would be 4 factorial, or n minus 1 factorial. So some people have a preference there. They think, I like to just divide by the number of people because that's how many rotations there would be, or I just take one less for the number of people for factorial. So it's whichever way is more comfortable for you, but in a circle, things behave differently than in a line because we have that repetition idea. All right, so let's see if you can recognize that in a couple other ones. So a carousel type caddy, so if you ever remember seeing these where it's just basically something that spins around that you can put like markers and pens and pencils and things in. It holds 14 different colored markers in a circular arrangement. How many ways can the markers be arranged? So if you're thinking about your 14 things in a circle, I want you to think of the idea of a circle. I know when I draw it, you have to show it this way. But technically for a circle, there's no beginning and there's no end. So I have these 14 different colored markers being arranged around this circle. I'm sure that's probably not 14, but you get the idea. All those rotations, all 14 of those rotations would look identical. There's no beginning, there's no end. I would be thinking if there was a beginning and an end, like a line, there'd be 14 factorial ways, but I have to divide out those 14 rotations that would all look the same. So what it really ends up to be then is 13 factorial. You can calculate the number if you'd like to be able to see that, but it's just the idea of which number factorial are we talking about. So this is definitely a circular arrangement. Now, don't get hung up on the idea that it has to be a pure circle. If I just said I had these markers sitting around a table, the table could be the shape of a rectangle. It's the ordering with respect to each other that's the important part of it. So don't get hung up on the fact that, oh, the table wasn't circular, so it's not, or the caddy wasn't circular. It just has to do with there's no beginning to your arrangement and there's no end to it. So a circle is a great representation for that. The shape of a circle has no beginning and no end. So it's not with respect to anything. Second one, a restaurant has 11 bowls on one of those circular revolving trays in the center. Some people call them like the lazy Susan, right? It rotates around. You can serve yourself from each of the bowls by just spinning that little circular tray around in the middle. How many different ways can the bowls be arranged? Well, again, they're arranged on a circle shape, no beginning, no end. We have these 11 bowls. I'm sure that's not 11 again, but we have 11 bowls going around. And if we rotate, we're going to be able to get the thing to eat that we want to, but we're not changing the ordering of the bowls. They're still next to the same ones that they were. And we have the idea that that ordering is going to be the same and it would be repeated. So if I just put them in a line, it would be 11 factorial. But since there's no beginning or end to this and all those rotations look the same, I would have to divide by 11, which would leave me with 10 factorial. And again, you can calculate that number if you need to. So looking at situations that are circular are really important to be able to distinguish that it is different. Okay, well, let's take it a step further then. What if you have circular permutations that have a fixed point? Okay, so what I'm going to show in class is basically two different bracelets. So I want to talk about that so you can at least get a visual of what I'm going to talk about in class. One bracelet is like those candy necklaces. So there's no starting point, there's no stopping point. We just have beads on it. So I'll just make my cute little bracelet here. So there's beads on my bracelet, but there's no beginning, no end. That's our circular, just regular circular permutation. Now, what if instead of a bracelet like that, like your candy necklace or whatever, what if instead of that bracelet, I have a bracelet that has what we call a fixed point. So when I make my bracelet, so I have this circular thing, then on the end of it, they have some sort of a clasp that holds it together. So we'll have, that's my little clasp. So on my bracelet, I have my beads. Okay, but I have a clasp. Now what the clasp means is I can unhook it, so I have a clasp, and my bracelet could end up being, so here's all my beads, a straight line. Because if you have a clasp, it means it's starting somewhere and it's stopping somewhere. It's just like a line. So this is what we call a circular permutation with a fixed point. You might be going around something, but you can actually unhook, or there's a definite like beginning and ending point. In this case, it'd be where the clasp is, where I'm starting with respect to that location, which means ultimately it's really just the same as putting it in a line. You're starting at that location, which means it's really just n factorial again. So we have the number of things. This, in this case, with my bracelet, I think I have 6 beads on there. It would be 6 factorial in a circle, or people sitting around a table, if you want to think of it that way. So with respect to something. So if it's a circular permutation with a start or an end on that fixed point, then it's just like a line. Okay, so take a look at how that might look differently in a situation. So there's 4 chairs around a table. Okay, so we have 4 chairs around a table, but one of them has armrests. So we'll make some armrests on there. All right, so how many ways can you put people in those seats relative to the chair with the armrests? Okay, so in this situation, we're talking about around something. So this is a circular permutation. So we're going around the table. But think of your armrest like your fixed point. That's where you're starting from. So because it's relative to something, that means we're starting and stopping with respect to that one chair. So instead of being dividing out those other rotations, they are actually all different. It would just be 4 factorial or 24 ways that I can do this because of the fixed point. Now, how could I change the question to make it not a fixed point? I could have just said, how many ways can you arrange 4 people around a table? Well, then it would be just like our people standing in a circle, and all those rotations would be the same. I would have to divide by 4 then to divide out all the ways that are alike, and I would just be down to 3 factorial then. So if there's not a fixed point, we're back to our straight circle situation. If there is a fixed point, then we're back to a line because it definitely starts somewhere and stops somewhere. All right, let's try another one like that. So there's 11 people that are going to be seated around a table where one person is seated closest to the exit. Okay, so we have this circle, and we have, ooh, that's a terrible circle. And then we have the exit door over here. And so there's a chair that's closest to the exit, and then we have our other 11 chairs, or 10 chairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we have our chair that's closest to the exit, and then we have our other 10 people. So how many different ways can we do this? Well, again, relative to the exit is your key phrase to understand that, oh, there's something special about that location. I can start or stop my orderings from there. So with respect to the exit, think of that like your fixed point, like your clasp on a bracelet. So when I look at that, I have to take into consideration then that this is really just like a line. Circular with a fixed point is just like linear. So this would be 11 factorial ways I could seat them. Now, if there wasn't that relative to the exit, if I changed the question to be, hey, how many ways can you put 11 people around a table? That would be 10 factorial, or 11 factorial, divide out the 11 ways that those rotations are all the same. So when we think about this, we really have to look for that idea of fixed point. Okay, our one last thing that we need to deal with, which is going to be super hard to show to talk about without having a visual, is this idea of reflection. Now, not every object has this reflexive property, but if you think about orientations of things that look the same, if you take a bracelet that has beads, so imagine a beaded bracelet where all the beads are identical, or say you have even different colors, but they're all the same shape and the beads themselves look the same. They have a reflexive property that if you lay them down and you draw a line right through the middle of them, the one half looks exactly the same as the other half. They're reflective over a line. So think like a parabola is reflective over a line. Same idea. So the orderings, if you look at the orderings of them, I'll use labels. Say you have A, B, C, and you're looking at what those labels would look like. If you reflect it, you end up getting CBA. But that ordering, if those beads are the same, is going to look exactly the same. It's identical. So when you think about something that has reflection, where they look the same, if you are looking at all of those different orientations going around, or even if it's linear, you can do the same thing. If you have ABC and you look at the reflection and you talk about CBA, if those beads are alike, if they are similar, then we're going to be overcounting. We have that reflexive idea. So anything that when you flip it over looks the same, we have that reflection issue. So there's not that many things that we'd be talking about for this. It would be like in your textbook, beads, charms, keys, things like that. Now in reality, we know not every bead, charm, or key looks exactly the same on each side, but that's the sort of the idea of it. If they are looking similar, that reflection would give you the same ordering of things, then we have to divide by 2 because each side looks identical when you flip it over. It looks the same as one of the original orderings. So the picture would look the same, or the list would look the same. So this can happen when it's linear, which remember is the same as circular with a fixed point. Those are the same thing. We can have reflection for beads, charms, or keys, or also just straight up circular and -1 factorial. You can have reflection as well. So we're going to assume that if you see beads, charms, and keys, people aren't reflexive, chairs aren't. Things like if you flip it over on the other side, it would be upside down. It wouldn't look the same thing. But for things like beads, they're spherical like that. They're going to look exactly the same. All right, so let's take a look at 2 examples then to illustrate this. The difference between the top and the bottom. See if you can take a look at these two and decide what's the difference between the example on the top and the bottom. Pause the video if you need to. So I'm underlining something here. With a clasp means you have a circular arrangement, so it's circular with a fixed point. So when I think about that, what that means is it's basically the same as linear. So you could actually really think of that circular with a fixed point as being basically the same thing as linear. If it's easier for you to go back and think for this one, yeah, that's linear. It means the same thing as it being in a line. That's really what we have going on here. It's linear. So that means it would be 6 factorial number of ways to arrange these beads because we can unclasp it and lay it out in a line. However, because it's beads, we're assuming that they're reflective. So we have to divide by 2 because otherwise those arrangements would be double counted. So we'd have 720 divided by 2 or 360. Now the ones on the bottom, it says without a clasp. That means just it's straight. I shouldn't say straight, that's funny. It's just circular, so it's just a circle. There's no beginning, there's no end. So I really do have to divide out by the number of ways to arrange 6 beads. So that would be 6 factorial divided by 6 or 5 factorial. But then again, because they're beads, they are reflective, I would need to divide by 2. So it'd be 120 then divided by 2 or 60 different ways. So when you're looking at doing arrangements like this, we really have to look for those nuances in the language or in the situation when you're looking at a real situation. So is there a beginning and an end? Is there a fixed point or isn't there? That's really important when we're looking at circular situations. And then for repetitions, when going back to what we talked about first, if things are repeated, we need to not overcount for that as well. We need to divide that out. Or if things are reflected, they look the same on each side, then we need to divide by that as well. We don't want to be overcounting, and we can't figure out likelihood, like things like probability, until we know how to count, until we know how we can figure out the total. So it's really important to start here. All right, so that wraps up kind of our counting piece of it. We'll be moving on next to dealing with actually being able to calculate things like likelihood, probability, odds.